Good morning. Happy Friday. All right, let's see here. There. Oh, okay. So I decided to make a little change. Let's go to this week here. Instead of power calculations, which you're welcome to read on your own, that was all in air quotes, you don't have to. I want to do ANOVAs today. Okay, so here, read on your own. I'll even put quotes here. And I'm going to emphasize that it's not tested. I know that's what everyone cares about. Oh, is it going to be on the test? No, it's not tested. I promise. So that's 7.4. Power calculations. Okay. It's interesting. It's how do you pick an appropriate sample size, right? That kind of thing for 2 sample means. And so it's good, but you can kind of read it on your own. And I'm not going to test it. So what I want to do today is I actually want to move this. So 7.5, which is ANOVA. Oops, if I can write. Oh man, ANOVA today. So what I want to do on Tuesday is probably finish up ANOVA, but then also I'll post some practice problems, mostly so that you can read them and identify the question. It's going to be like, do you guys know a mad minute? A mad minute is in grade school where you have to do 100 questions in a minute. You just go, go, go. It's like 7 + 5, blah, 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 blah. And a mad minute. Anyways, so just quick and dirty, identify what type of question it is, and then I'll post the solutions to those questions, and we'll work through some of them if there's any ones in particular that you want to work through, right? So we'll kind of use Tuesday, which I've opened up now, for kind of finishing up ANOVA and a little bit of review for quiz number 4. Okay, so then Tuesday here is likely going to be finish ANOVA. I'll put a question mark there. And quiz number 4, let's say practice. Right. Practice / review. Just so you know, and then we'll start regression chapter 8 on the Thursday, which is not on the quiz, right? So we've got a little bit of a breather, unlike all the other quizzes, right? So you've got time to practice. I'll post the ANOVA assignment today so that you'll have the weekend to work through it. It's going to be quite short. Well, I shouldn't say that. Then you guys put it off. Oh, she said it's short. What's short to me? Yeah, I'm like, short to me is probably different than short to you, because you've got other things going on. All right, so you guys saw I posted assignment 15. I think I mentioned it yesterday, right? Yeah. And then so assignment 16 is going to be ANOVA, and then those are the assignments, assignment 14, 15, and 16 for quiz 4. Okie dokie, artichoke. All right. Are you guys ready? So same pattern as before, right? We started with one sample mean, and then what's that? Hello? Anybody out there? Oh. I'm gonna mute you. There. Otherwise, it's too scary. There. Okay. Unless you had a question, then unmute yourself. All right. So, right. We started with one sample mean, and then we moved on to, okay, well, what if I have two samples, right? And the first scenario that we looked at was, okay, well, these two samples are paired, right? I'm making two observations on the same subject. We treat those, we boil it down to a one sample scenario, right? So that's why we started there. It's because we just regress back to our old ways of one sample means. And then yesterday we introduced, okay, well, so now what if I can't boil it down to one sample? What if I have to treat them as two independent samples? That's very common, right? And so today we're going to move on to, okay, well, what if I have more than two groups, right? What if I have 3, 4, 5 groups? Okay, and so 7.5 is called comparing many means with ANOVA. ANOVA stands for analysis of variance. Oops, should have an R in there probably. Oops. That's what ANOVA stands for, analysis of variance, which is weird because we're actually comparing means, right? But how we compare those means ends up relying on the variance within and between the groups. That was too much information, I think. But so here, comparing many means is when we're analyzing more than two groups. You can use it for just two groups, but then you should probably just use a two sample t-test like we did yesterday, right? And so depending on the scenario, right? If you have less than 3 groups, then you should probably just use a t-test. Okay, so where do we begin? I'm gonna do a snack-sized version of ANOVA. Okay, we're just gonna touch the surface, figure out how do we read some output, what does it tell us, right? And then, of course, if you're gonna do any more stats, then we'll do more ANOVAs later, especially if you're doing stat 240, or if you're doing regression with Claude, that kind of thing. Then you'll do more ANOVAs. Or I think if you're in the biology side, you'll do ANOVAs with CAM, that kind of thing. So you will see more ANOVAs. We are just touching the surface. Okay, so an ANOVA is kind of a fun concept. The way I think about an ANOVA is if I have more than 2 groups, let's say I have 3 groups. So let's say we want to compare the means of 3 groups. A, B, C, let's say. It might be tempting to say, okay, well, I know what to do. I can just compare these pairwise, right? What if I just use a 2-sample t-test and compare A with B, but then I'd have to compare with A with C and then B with C, right? And so here I say it might be tempting because that's not what we should be doing, right? And so it might be tempting to conduct individual pairwise comparisons. To conduct individual pairwise comparisons. Oops. Right, so things like A with B, A with C, oops, B with C. Right, that's 3 pairwise comparisons. Right, I did all the combinations, right? A with B, A with C, B with C, yeah. So I could do a 2-sample t-test, right, for each of these, right? So here, this would be 3 individual 2-sample t-tests. The problem is that each time that we do this pairwise comparison, never mind that it's tedious and annoying, right? Okay, now on to the next one, now on to the next one, right? Especially, let's think about what if you have 5 groups, right? How many pairwise comparisons are you doing then, right? That's annoying, right? And so, but not just annoying, the problem is that each time that we do this t-test, we open ourselves up to a type 1 error, right? Each time that we run this, right, we're opening ourselves up and saying, okay, well, there's a probability of making a type 1 error. The alpha level is the probability of making a type 1 error. So now the probability of making a type 1 error is no longer 0.05, right? It's 0.05 plus 0.05 plus 0.05. So now all of a sudden, and remember, a type 1 error is rejecting H0 when it shouldn't be rejected, right? And so really what that's saying is that, okay, well, if you do enough pairwise comparisons, you will find a significant difference somewhere, right? Not necessarily because it exists, right? Just by random chance alone. And so I'm not going to dwell on that, but that's the backstory. And so here, each pairwise comparison introduces the same probability of making a type 1 error. Oops, error. So that's a problem. Okay. And if we think back to when we didn't have computers and you were doing all this by hand, right? Remember what goes into a t-test, it requires that we know the sample means and the sample standard deviations. So let's say we have 5 groups, right? A with B, A with C, A with D, A with E, right? So on and so forth. To do all those pairwise comparisons means that we need the mean and the standard deviation for each of those samples. That's crazy, right? If we don't have a computer, that's going to take a long time. So what we do instead is, or where ANOVA's stepped in, is ANOVA's, I imagine it kind of peeking into the box of the means, and it's going, hey, anyone significant in there? And then if the result of the ANOVA is significant, then it's saying, yes, there is something worth finding in there, right? You still have to go find it, right? But having this kind of tool where we can look in and be like, is anything going on in here, right? Or is there nothing worth pursuing, right? And so that's kind of how I think about ANOVAs. Is anybody home? And so ANOVAs don't tell us which pairwise comparison is significant. It tells us if there is one mean that's different from the others. Okay. Or at least one mean. So ANOVAs do not tell us which mean, potentially more than one, which means are different from the others or are significantly different from the others. But it does tell us if there is a mean that's different, or at least one mean that's different from the others. If there is at least one mean that is different from the others. Yeah. We start out the same way that we have been for all our hypothesis testing is, okay, well, we're going to assume that all the means are the same. Okay. But then our alternative hypothesis is going to be that, okay, one of these means is not like the others, right? It doesn't tell us which one, right? That's going to need more exploring. And that's when we would go back and potentially do these pairwise comparisons, but we make adjustments, right, to reduce that type 1 error, right? So, but we're not there yet. Okay. So let's see here. There was a blurb I wanted to grab here. Wow. Okay. So in the case of ANOVAs, it's like the textbook says it best. I was just going to write all this out, but then I'm like, no, I'm too lazy. Okay, so an analysis of variance is going to be a hypothesis test. We are going to have a new test statistic, which is the F test statistic, which means that F has its own probability distribution, right? It is built into that probability calculator that we have, right? And so that's nice. But we are going to have a new test statistic. We are not going to have to calculate it. Maybe some brief calculations. I'll show you how. But it'll be given in a table, so don't worry. Okay. The null hypothesis for ANOVA, like we said, is that the mean outcome is the same across all groups. We mean same in the sense that they're not significantly different from each other, right? They're all kind of in the same realm and nothing significant is happening there. If you want to use notation, right? If you have K groups, then you would say that mu1 is the same as mu2, which is the same as, and that's where we were yesterday, right? mu1 equals mu2. That was our hypothesis, right? And then now we're just adding on more means up to K means. Okay? Which sounds weird if you've done K means clustering, maybe in 300 or something like that. Yeah, but that's not what I mean. here I'm just, K is just a variable for the number of groups that you have, okay? So mu I generically represents the mean of an outcome for category 1, or I rather 1. K is the number of groups. Or categories, I should say. Just because, oh no, they do use groups, but then they use categories. We can use them interchangeably, right? The alternative hypothesis is that at least one mean is different, right? So that's what I mean. It's just going to be like, yep, something is happening here, and then we pursue it, okay? But it's really nice to have that check-in point, right? Imagine if you're doing this all by hand, right? If you can calculate this ANOVA to see if there's anything worth finding, right? And then it says, no, there's nothing here. Then you can move on with your life. Okay. What's nice is this will always be the null and alternative hypotheses for ANOVAs. Okay. So the mean outcome is the same across all groups. You could fancy things up and say the groups of what, right? I think the examples in the textbook are across different classes, right? So there's kind of 3 classes that have different teachers, different TAs that they're comparing the grades of, right? I know there's a really common example of the chicken feed. So what type of food are you giving these baby chicks? And then how much weight do they gain, right? That kind of thing. And so then you have different foods, right? Always remember that we're talking about the mean, right? The mean outcome is the same across all groups. Okay? So we're just comparing averages across more than 2 groups. Okay? And so here, I'll make a note. This will always be the null and alternative hypotheses for ANOVA. So these will always be H0 and HJ for ANOVA. As I say that, I think of a scenario where that's not true, but we're not there yet. So for now, that is true for us. Oh, okay, fine. For us. Only because if you are doing multiple regression, which is just fitting a line, right, then you're going to have multiple coefficients, and the coefficients, you test them using an ANOVA as well. That's fine. Just ignore what I just said. We're going to use ANOVAs in different scenarios, just like we used Z for different scenarios, right? 1 sample proportion, 2 sample proportions. We use T for different scenarios, right? 1 sample mean, 2 sample mean. So it makes sense that we can kind of flex ANOVA a little bit as well, or the F test. Okay. I'm going to mention the conditions, but for ANOVAs, for us, I'm just going to say you may assume the conditions for inference are satisfied. Okay, so I'm not going to make you check them, but of course we should say them out loud once. Okay, and so there's 3 conditions. Okay. The first 2 are the same as what we've been doing so far. The observations are independent within and across the groups, remembering that now you have more than 2 groups, right? But same idea. How do we ensure that? Random sampling, right? Or random assignment if it's an experiment. The second one is that the data within each group are nearly normal, right? That's the same as what we were checking when we checked, okay, if the sample size is less than 30, then I need to make sure that there are no outliers, right? That kind of thing. Usually for an ANOVA, you would do side-by-side box plots, and you can look at those. And if the box plots are kind of relatively symmetric, then you're good, right? But these two are same as the t-test. Okay. So the only new one that we're adding on is that the variability across the groups is about equal, which means that, okay, if you have a box plot, right, you need to make sure that they're roughly the same width, right? Because you can't have something with very little variability and compare it to something with huge variability. And the ANOVA just doesn't work in that case. Okay? And so here, this I guess is the new one. New for ANOVA. To check that the variability across the groups is about equal condition is satisfied. We usually consider side-by-side box plots. So I just want to show you what that looks like. Here they've done dot plots. It's kind of an exercise in, can you tell the difference between these groups 1, 2, and 3 versus 4, 5, and 6. Okay. But I think the box plots make it a little bit easier. So for example, now I don't know, is it baseball? On base percentage, who knows? I know, bad. I don't know what these stand for. If I had read this example more closely, I would know. Catcher? I'm getting a nod, so it's pretty good. Okay, so what are we looking for, right? If we're looking for the variability across the groups is about equal, well, then we're looking at, I wish I could have like a double pointer on here, right? We're looking at just overall the variability here. Is it roughly the same for all these groups? I would say yes, right? There's some outliers, but we're a little bit flexible here. As long as there's nothing glaring, then it's okay. Okay. And for the normality condition, right, it looks like everything's roughly symmetric about the mean, right? And for all of these, and so that's okay. Okay. And I'll just kind of the variability across groups. Oops. Oops. Is about equal. Okay. So I need to bring this in here. bump it to the top. I want that output. Okay, so there is lots and lots of theory that goes into ANOVA, and we are ignoring all of it and just getting straight to the output. Okay, but it does analyze the variance. Okay, and so it is taking all kinds of information into account to generate this F statistic. And of course, it's here, but the newest thing about the F test is that it has two sets of degrees of freedom. It's going to have the first degrees of freedom and the second degrees of freedom. And that's going to dictate the shape of the F distribution. So the F distribution is another skewed distribution, just like the chi-squared. It's just shaped a little bit differently. And it has these two sets of degrees of freedom. Okay, just like the chi-squared, it's just the upper tail area that's the p-value. Okay, so very similar to what we saw in the more than two proportion scenario, right, so far. Okay. I'm going to grab this here. I know I have not told you what the F statistic is, and that's on purpose. Okay. So ANOVA uses a test statistic F, which represents a standardized ratio of variability in the sample means relative to the variability within the groups. Just blah, 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 ignore that. Don't ignore it, but we don't need to focus on it. If H naught is true and the model conditions are satisfied, then F follows an F distribution with degrees of freedom 1 is K minus 1, okay, which is the number of groups minus 1. And degrees of freedom 2, N minus K. Okay. So your total sample size minus the number of groups. Okay. And then the upper tail of the F distribution is used to represent the p-value. Okay. Now, let's look at some output. Okay. This is using that, I think is it Major League Baseball data? The beauty of stats is I don't really need to know what it's about. So here, well, I need to have some idea, I guess. Okay. ANOVA output looks like this. Okay. And so you're going to have some generic name for the groups, right? In terms of that baseball example, you had, what did we decide? Outfield, infield, catcher, or C, yeah, TBD, right? But some generic term for the groups. I want to actually blow this up, but how about, right, this is some generic term, or I shouldn't say generic, I should say a general term, general group name. How about that? So you've got some group name. You're also going to have information on the residuals. Yeah. We have the degrees of freedom 1 and degrees of freedom 2. Okay. And maybe I will break this up here. So here, this is going to be degrees of freedom 1, degrees of freedom 2. We can also do a total down here, which is going to be for the degrees of freedom, it's going to be the degrees of freedom 1 plus the degrees of freedom 2. We'll have information on the sums of squares. We're not going to talk about what they are. I know it's all hand wavy. Oh, and you know what? I want to just ignore this lower part for a bit there. Okay. Sums of squares, though, you're going to have sums of squares for the groups and the residuals. And in terms of the total, you can add down the column again. So here, this becomes SS. Usually we call it G plus SS. And maybe I'll just use G and E. Right. So here, this is the SSG and SSE. You could say 1 and 2, but that would hurt me too much. But yeah, absolutely. For our purposes, right, we just need to know the anatomy of this table, where things are coming from. Okay. And so if I call this MSG for the groups and MSE for the errors, which for some reason we say errors when we are talking about the residuals, why not just say errors here? I don't know, but that's just how it is. Okay. We don't worry about the total down here because what we do, F, this is your F, and F, let's use a different color here. F is MSG divided by MSE. Notice how it's this one divided by this one. So they're basically set up as a fraction already. Okay. What's cute is that the MSG is the SSG divided by the degrees of freedom. So there's kind of a tandem situation going on here. The MSE is the SSE divided by its degrees of freedom. Okay.
So we expect a greater value of F.
Yeah. So if the larger F is, the more likely you're going to reject the null hypothesis. Yeah. And that's because the group variance is larger than the residual area. Yeah. But it also gives you the p-value for the F as an output. I'll show you how to find it, but right here, this is the p-value. The p-value for the ANOVA.
And we expect a tiny p-value.
Yeah. If you don't get a small p-value, it just means that there's nothing happening in there. Right? So when I say, okay, we're going to go in here and in terms of these baseball positions, is there a difference in whatever we're measuring, the on-base percentage? Hello, anyone different in there? Then this small p-value tells me that yes, there is a position or more positions that are different from each other, right? And so we're usually expecting to reject the null hypothesis if we think there's something going on, right? Yes?
Is it okay if you write it down? MSG?
Yes. Yes. So here, MSG is the SSG divided by DF1 or DFG if you prefer. And the MSE is the same. So it's kind of this this fun snake through, right? As long as you have a couple of these components, and I do have a question on the assignment where you have to fill in, you've got enough information there and you need to backtrack and figure out, okay, for example, knowing the total and knowing one of these two, you can fill in the other one, and then, right, you can kind of fill in the missing pieces. Okay? And it's kind of this, this fun snake thing going on. Good. So given output, right, from here, right, we have the p-value. So we have the test statistics. So this is basically step 2 of our hypothesis test. Remember, the null and alternative hypotheses are always mu1 equals mu2 equals mu3 up to however many groups you want to compare. And the alternative is that at least one of these is different. Okay. Then in terms of step 2, right, do the test. Well, you're going to have this output here, and the test statistic is the F, 5.0766. All right. And again, a large F usually means you're going to reject the null hypothesis, right? But it depends on the degrees of freedom. So then it also gives you the p-value, which is your step 3, right? And so we can also, whoops. We can also find the p-value using the probability calculator. Just remembering, okay. I'll need my, I'll go in here.
I'll have a quick question.
Yes.
So to do the,
Oh.
to reject the null hypothesis, we use the, we compare to the F value, right? We have to calculate the P value.
Well, the p-value is going to be included in the table. So you'll just have the p-value. It's just, I want to show you in this thing that's not working right now. I should have restarted. I knew it. Hello. I want to show you that you can find the p-value, just so that you have those tools. And of course, right, now that I've ditched the tables, this would have been another table for you to keep track of. Oh, yikes, right? That means there's a Z table, a T table, an F table, a chi-squared table, and lots of other tables. But we don't need them anymore. Sorry, I just need to go back there. Maybe. I access it through the assignment because that's the only way that it shows up completely. I don't know how to fix that, but I guess that's the only place that we need it. So in the distribution tab, we are now working in the F distribution. Okay. Notice how, if you think about it in terms of tables, right, all these old school tables that you would have had, there would have been a table for all of these distributions. Yikes. F distribution looks like what we saw, right? And then we need degrees of freedom 1, which in this case was 2. And I think it was 426. And the p-value is the area in the upper tail, right? So I need to change that to the upper tail. Come on. And I think I had 5 point, anyone remember? 0766. 5.0766. Come on. It doesn't want to show us the distribution. I guess because it looks like this,
That's fair.
I guess. I think it's because the degrees of freedom too is so large. So here. So here we have the F distribution. We enter the degrees of freedom, and I guess it dropped one. And then the area in the upper tail. Upper tail is the p-value. Right, but this 0.06, so sorry, 0.0066, right, that is the same as what we had, what we were given in the table. So you can use that probability calculator to find it. However, it will be part of that output, right? Okay, so using that p-value, right, we can state our conclusion, right? Same idea as always, right? So if the p-value is less than the alpha level, then we have enough evidence to reject H naught, right? In this case, we have enough evidence to reject H naught. And now we can say that there is at least one position that is significantly different from the others, right? We don't know how many, right, or which ones, but there is at least one of the groups that's significantly different from the others. Okay. So then in terms of our, I'll call it step 4. I didn't outline the other steps, so that's confusing, but the conclusion, right? Since the p-value of 0.0066 is less than the alpha level, I'll say the assumed alpha level of 0.05, we have enough evidence to reject H naught. In favor of HA. Therefore, the mean of at least one of the groups, I'll do it generically. The mean of at least one of the groups is significantly different from the others. That's the ANOVA. I know I'll get you guys to work through some assignment problems because we only did one basically. After this, right? So knowing that there's at least one group that's significantly different, then we're going to do those pairwise comparisons, but we're going to have to make adjustments based off of the alpha level, right? I don't want to introduce an alpha of 0.05 every time I do it. And it's called the Bonferroni adjustment. So something to look forward to on Tuesday. If you have any questions, let me know. Otherwise, have a wonderful weekend. I'll see you on Tuesday. I'll stop this recording here.
Awesome.